and welcome to Arithmetica, and the first video on our program on a brief account of mathematical logic, where I shall be presenting a number of episodic videos covering its general development and of those of whom made a significant contribution to the field. As the title would suggest, the videos serve more as an overview of the study of mathematical logic. However, I will be providing an historical account together with some mathematical details. Strictly speaking, this is not intended as a teaching aid, but rather to serve, among what I have already commented on, as establishing a setting for this channel and the type of content you might expect to find here. So, without any further ado, here is the introduction to a brief account of mathematical logic. The systematic study of the philosophy of logic and that of its intrinsic connection to language has ancient roots. Indeed, its recorded origin stems at least as far back to the work of the Greek philosopher Aristotle, of whom is often referred to as the father of logic. Aristotle's momentous work on logic took the form of 6 books on logic and scientific methodology, including his writings on deductive reasoning, known as the Prior Analytics, which became known as his syllogisms. So, what exactly is a syllogism? Well, Aristotle's notion of a syllogism is a process of logical deduction, where the conclusion is supported by 2 premises, a major premise and a minor premise. A syllogism can either be sound or valid, the distinction being that it is sound if the conclusion exists as a logical consequence of true premises, while a valid syllogism is of a weaker form, and only requires the conclusion to be a logical consequence, irrespective of the truth of either of the major or minor premises in force. A simple and frequently used example of a sound syllogism is where we take the major and minor premises to be, respectively, all men are mortal and Socrates was a man, both of which are clearly true. We can then provide the logically valid and sound conclusion that, therefore, Socrates was mortal. An example of a valid but unsound syllogism is in taking the major premise to be all elephants are pink and the minor premise as Nelly is an elephant. A valid but arguably unsound conclusion would therefore be Nelly the elephant is pink. Generally, an unsound syllogism can only be valid if at least one or either of the major or minor premises is false. Aristotelian logic flourished through the ages and eventually developed into the dominant form of Western logic until the advances of the various branches of the field and the relating works of philosophers and mathematicians. And of particular note was the famous 17th to 18th century German philosopher and mathematician Gottfried Leibniz. Leibniz was arguably one of the most remarkable mathematicians and philosophers of his time. He is well known for his independent work paralleling Isaac Newton's development of the differential and integral calculus, as well as his profound interest in philosophy. In particular, he was highly motivated with his idea on developing a universal language in the mechanization of solving problems by calculation alone, whether the topic was of a mathematical, philosophical, or even sociological context. This included his famous question on determining the truth of any statement in number theory, simply by putting pen to paper and carrying out a finite series of steps leading to the answer. Today, such a mechanized process would be referred to as an algorithm. Thus, in contemporary language, we can rephrase Leibniz's question as, is there an algorithm for determining which statements of number theory are true? Indeed, it was not until the 20th century when this question was answered, thereby justifying in fulfilling one of Leibniz's hopes in his disclosure, I have so many ideas that may perhaps be of some use in time, if others more penetrating than I go deeply into them some day, and join the beauty of their minds to the labour of mine. In fact, his fascination with mechanization led to his design of the Leibniz wheel in the year 1673, otherwise known as a stepped drum, consisting of a series of teeth on a cylinder, which, when connected to a counting wheel, Leibniz was able to construct the stepped reckoner, a calculating machine capable of the arithmetical operations of addition, subtraction, multiplication, and division. Indeed, in 1685, Leibniz explained the value of his calculating machine to the astronomers of the time, when he stated that it is unworthy of excellent men to lose hours like slaves in the labour of calculation, which could safely be relegated to anyone else if machines were used. It remained the only workable solution to machine calculation until around 1875. Indeed, such a mechanised process was not replaced until as late as 1947, when Cortina Limited of Liechtenstein began production of a handheld calculator by the Austrian engineer Kurt Hertzog, which he had designed in the 1930s. Although based on the same stepped drum mechanism of Leibniz, its small, simple hand-cranked design attracted a lot of interest and boasted not only the same basic arithmetical operations as Leibniz's stepped reckoner, but in addition included more complex operations, including the calculation of square roots. It was eventually replaced by the electronic pocket calculator during the early 1970s. It is this manner of philosophical thinking from philosophers like Leibniz which encouraged the further development in reasoning, inclusive of the study of mathematical logic. During the 19th and early 20th century, an attempt was made to further the philosophical setting for the foundations of mathematics. Primarily, this took the form of three schools of thought: formalism, intuitionism, and logicism. Formalism is often accredited to the German mathematician David Hilbert. It describes an emphasis on form over content or meaning, claiming that formulas are intrinsically meaningless, and insists that mathematics is no more than the syntactical manipulation of symbols in accordance to accepted rules. As a consequence, formalism lends itself very well to axiomatic systems, despite it not being the accepted standard of mathematics. A general argument against formalism by those who do not support it is that there are some things in mathematics that are inherently true, irrespective to the symbols within mathematics and any rules imposed on them. This argument draws our attention to the various applications of mathematics, where we have an understanding of the meaning of numbers, and that formalism fails in considering the analysis of mathematical concepts. Intuitionism in mathematics takes on the idea that mathematics is the creation of the human mind, and that mathematical truth is conceived purely via proof by constructive mental processes, as opposed to the existence of fundamental principles within an objective reality. When two people communicate mathematical concepts, intuitionism claims that such communications simply actualize the means to create the same mental processes, but in different minds. It was introduced by the Dutch mathematician Lutzen E. J. Brouwer, and despite still being studied today, intuitionism takes a significant deviation from classical mathematics. This includes the rejection of the law of the excluded middle, which asserts that for all propositional formulas of mathematics, the disjunction of such a proposition and its negation is a logical truth. However, the accepted standard of the foundations of mathematics is that of logicism. It was formally introduced by German logician and mathematician Friedrich Ludwig Gottlob Frege, and Welsh logician and mathematician Bertrand Russell, among others. Logicism is the thesis that all of mathematics is reducible to logic, beginning with concepts of propositional calculus, governing the rules of deduction and that of logical operations on sentences. These include the logical connectives such as the negation, conjunction, disjunction, or conditional operator. Logicism, therefore, as one might expect, is at the very heart of the formal development of the study of mathematical logic. Mathematical logic began its formal development in the mid-19th century, concerned with the application of formal logic, inclusive of proof theory and that of formal systems in deductive reasoning in establishing formal proof to mathematics. It has close associations to theoretical computer science and that of the study of algorithmic computable functions and recursion, for which, according to Church's thesis, the two correspond, so named after the American logician Alonzo Church. With its foundations including, but not limited to, the work of the Italian mathematician Giuseppe Peano, who was renowned for his introduction of much of the now standard notation in logic and set theory, for which set theory is often regarded as the language of mathematics. Peano is famous for his 1889 publication, The Principles of Arithmetic Presented by a New Method, which included his so-called Peano axioms for the positive integers, otherwise known as the positive whole numbers, i.e. 1, 2, 3, 4, 5, and so forth. Peano developed his set of axioms for the theory of positive integers by employing a variation of the logical systems of the mathematicians and logicians George Boole, and who later extended the work of Boole, Ernst Schroeder, both of whom had made contributions to the development of formal systems, such that Boole is perhaps most notable as the author of the 1847 publication, The Mathematical Analysis of Logic, where he argued that logic, rather than philosophy, should be allied with mathematics, and proceeded in modernizing the Aristotelian system of cataloguing the valid syllogisms by instead providing general algorithms in an algebraic language. This then gained him the support from the English logician Augustus de Morgan, of whom is famous for his so-called De Morgan's laws, used in both set theory and propositional logic. Later, Boole published an investigation into the laws of thought in 1854, where he sets himself the task to express purely philosophical arguments into symbolic form, and which included his famed work on Boolean logic and its algebraic companion, as well as analytical methods in theoretical probability. Boole's work has led to many modern-day applications, including electronic computers which use binary digits and logical elements that rely on Boolean logic for their design and operation. The Peano axioms includes first-order statements concerning equality and that of the successor operation, which for the positive integers, the successor of an integer n, say, is simply the sum n plus 1, that is, adds 1. The only second-order statement is what is generally referred to as the induction axiom. It is called second order because it is a two-sorted first-order language, such that it contains two sorts of variables, number variables and set variables, i.e. predicates may be interpreted as sets of sets. In contrast, first-order logic, or first-order predicate calculus, uses quantified variables where the predicates are often associated with sets, but not sets of sets. Now, before we continue, let's provide further clarification on some of the terminology just used. A variable in mathematics generally denotes an arbitrary or unspecified mathematical object, such as a number, and can take a range of allowed values as opposed to a constant, which is fixed. I have also spoke of sets. A set is a well-defined collection of mathematical objects called the elements of the set. One example is the set of natural numbers, which in mathematical logic are the non-negative integers and is usually denoted by the double-struck capital N, or in curly brackets showing the first few elements in ascending order, followed by an ellipsis. So we could write. Another example would be the set of axioms of a formal system, for which I will detail in a later video. I shall also refer to the concept of a subset. A subset of a set X is any collection of elements that are in the set X. As an example, since all natural numbers are real, the set of real numbers, denoted by the double-struck capital R, has the set of natural numbers as a subset. And because not all real numbers are natural numbers, we say that the set of natural numbers is a proper subset of the set of real numbers. That is, there are elements in the set of real numbers that are not in the set of natural numbers. Moreover, by the definition of a subset, it is also trivially true that every set is a subset of itself, but clearly not a proper subset. In a later video, I will also introduce the concept of a class, which is related to sets. Later contributions to the field included the works of the German mathematician Ernst Zermelo, best known for his well-ordering theorem in set theory, as well as his development of the Zermelo-Fraenkel axiomatic set theory, a set of axioms inclusive of the axiom of replacement as proposed by the German-born Israeli mathematician Abraham Fraenkel. It was built upon an earlier system by the aforementioned German mathematician Gottlob Frege, whose work over the years increasingly focused on the foundations of mathematics in set theory. Axiomatic set theory can be seen as the systematic process of capturing mathematical notions and theories and reducing these to fundamental logical concepts. If then set theory can be perceived as a component of logic, it follows that such a reduction is consistent with the logicist's aim. Frege's contributing work in logicism included his conceptual notation of 1879 and was his first publication that included his development of quantifier logic, and where he detailed a logical system in which mathematical statements could be derived. The following two publications, The Foundations of Mathematics of 1884 and The Basic Laws of Arithmetic, in which the first volume was published in 1893, provided the formal setting for his axiomatic system of set theory, so designed to establish a complete reduction of mathematics to logic, and a description of how the theorems of mathematics may be derived. Unfortunately, in June 1902, when Frege was nearing completion of the second volume of his work on set theory, Bertrand Russell, the Welsh mathematician and logicist of whom we briefly mentioned of earlier, had discovered an inconsistency in Frege's system. Russell's letter arrived just as the publication was in press, and on realizing its implications, Frege promptly written an account of Russell's discovery to be included in the appendix. The inconsistency was owing to Frege's ill-fated Basic Law 5, a type of abstraction principle which asserts that the truth value for any two logical functions or concepts of their respective value ranges are identical if, and only if, they have the same value for every argument. If we restrict to the value ranges as arguments of mappings, then this seems perfectly plausible. However, it is possible to prove a strong theorem of class membership, which Russell shown can lead to a contradiction, namely the so-called Russell paradox, since it can be applied to the property of sets that are not members of themselves. Bertrand Russell's discovery of the paradox is largely influenced by Georg Cantor's work on the study of infinities and of his pioneering work in set theory. Georg Cantor was a brilliant German mathematician, of whom contributed to the development of naive set theory. He is most notable for his studying of infinity and his so-called transfinite cardinals, the notion of higher cardinal infinities. And it is the remarkable work of Georg Cantor, of whom I shall cover in the next video, on A Brief Account of Mathematical Logic.